Okay.
Yeah, it's our pleasure to welcome our speaker today, Ilya Kapovich, and he's going to talk about permittivity index bounds in free groups and the second Chebyshev function.
Thank you, Alina. Thank you, everybody who is here, and thank you those of you who are listening online. So I'll try to talk reasonably loudly. Hopefully, those who are listening on Zoom will be able to hear. This talk is based on a joint paper with Zachary Simon. The paper just appeared in iJack this year, so there is also an archive preprint available. So Zachary Simon was actually a master's student at CUNY at City College. So he recently graduated. Now he's doing AI research for the defense industry. And this was like a pandemic era research project, and it eventually resulted in this paper. So I never talked about it, and I decided that it's a good idea to talk about it here. So I'll give the statements of the two main results, and I'll explain, the various terminology, various terms involved in these statements later. So the first theorem says that the permittivity index for the element A and B n in the free group on two generators, that the sequence as the sequence depending on n is an unbounded sequence, and more specifically taking n to ni to be LCM of the numbers 1 through I, the permittivity index of A and I, B and I minus log ni, so it's little o of log ni. So that's the specific subsequence where we know that this quantity is unbounded. And then there is another thing called the simplicity index, and on the same thing, on a to the n, b to the n, it's actually, instead of being unbounded, it's identically equal to 2. So I'll explain what all of these things are, but these are going to be two main results. So there are various other results in this paper. So as I said, there is two main quantities here. This is the permittivity index of an element of a free group, a non-trivial element G of a free group of n, and the simplicity index. So these are the two notations. So I'll explain what they are, and I'll explain some kind of motivation. In fact, there are several motivations for these notions. Some of them, they are purely algebraic, some of them are sort of geometric or topological. So for me, the primary motivation was in fact topological and geometric, and it comes from untangling curves on surfaces, closed curves on surfaces. So here sigma is going to be a closed hyperbolic surface, so a compact hyperbolic surface without a boundary, sigma. So you should think about the surface as a cubed with a specific hyperbolic metric, and alpha is an actual closed geodesic, so which is typically in this problem is going to be non-simple, so with some self-intersections. So I can't really draw complicated closed geodesics which are not simple. So here is one which has one self-intersection, but we can try to draw more complicated ones. And there is a result of Scott from somewhere in the middle 1980s, which says that for any closed geodesic alpha on sigma like this, there exists a finite cover sigma hat of the surface sigma, such that alpha leaves to a simple closed geodesic in this cover sigma hat. So the proof of this fact involves subgroup separability of the surface group. So, but the geometric statement is the one I told you here. And there is a much more recent result, so this is like a classical result of Scott, and a much more recent result of Priyam Patel quantified this statement in terms of bounding the smallest possible degree of this cover in terms of the length of the curve alpha. And she proved that you can always do it, bound the degree of the cover basically by something which is linear in terms of the length of the curve. So this was already an interesting statement, and after that, so we started. And Gaster, Gaster actually proved his theorem already after my paper with Neha Gupta that I'll mention a little later, where similar questions were sort of studied for free groups. But one can then ask what the worst case sort of behavior of this degree function is if you look over all closed geodesics of lengths, let's say less than or equal than L. So what's the minimal degree where alpha sort of unwraps to a simple closed geodesic is, and how it depends on the length L. And Gaster proved that it depends linearly. That is to say that there exists sort of a sequence of such curves alpha where the worst case behavior is also linear. So that's what's known about untangling closed geodesics on hyperbolic surfaces. And let me just mention, maybe I'll say something about this later, is that these questions are also related to algebraic questions about quantitative aspects of residual finiteness of groups, where you have finitely generated residually finite group, and you're trying to understand, to bound the, let's say, the smallest size of a quotient, of a finite quotient, where a particular element G from which you start remains non-trivial in that quotient, and you try to bound it in terms of the word length of the element from which you started. So that's the kind of a question, that typically is considered, in this business of quantifying residual finiteness. And Khalid Bourabi did a lot of work on this topic, and in fact, he wrote an appendix for the paper with Gupta that I'll mention later, where some of the results related to primitivity and simplicity index are proved for free groups. So let me now explain what the analogous notions to what happened here and analogous results might be in the setting of free groups. So in the setting of a free group, we are going to think about the simple closed curve as being replaced by a primitive element, an element which belongs to some free basis in a free group. So we'll take that as a kind of our analogy. And by the way, there will be some confusion in terminology, you will see, because there is also the notion of a simple element in the free group, which means something else. I'll explain. So, but nevertheless, so the terminology here does not quite correspond to the to the geometric terminology for surfaces. So I'll say that an element of a free group is called primitive if it belongs to some free basis of this free group, and a non-trivial element is called simple in the free group, and that's the notion that's stuck, even though it sort of doesn't quite fit the notion from surfaces, if this element belongs to some proper free factor. That is to say, if there exists a decomposition of the free group as a proper free product, A star B, where both A and B are non-trivial, where this element X belongs to, let's say, A. So an element X like that is called simple in the free group Fn. And of course, primitive implies simple, but not the other way around. So for instance, if you take the commutator of A and B in the free group on A, B, and C, then this element, it's simple, but not primitive. So let me show this. So let me also recall a theorem of Marshall-Hall, which says that for every non-trivial element in the free group, there exists a subgroup of finite index H, which contains it such that, well, okay, it's not actually his theorem, but it is implied by his theorem. So Marshall-Hall's theorem implies that every non-trivial element of G can be made primitive in some subgroup H of finite index in the free group. So that's what follows. And we can think about this as an analog of Scott's theorem, which said that every curve becomes simple in some finite cover. So every element becomes primitive in some finite index subgroup. So, and once this theorem is known, and I'll give you like a cartoon proof of this in a little while, we can define the primitivity index of a non-trivial element as the smallest degree of such, the smallest index of such subgroup. So this is the minimum index of a subgroup H of the free group, such that it contains G as a primitive element. So this is called the primitivity index of G in Fn. And also we can define a smaller quantity, the simplicity index of G, which is the smallest index of H, subgroup of Fn, which contains G as a simple element. And as I said, because being primitive implies being simple, but not the other way around, so this simplicity index is a priori smaller than the primitivity index. And Marshall-Hall implies that they're both finite. So now there are some simple invariances, so it's easy to see from the definitions that, well, I wrote it here for the permittivity index, but the same with simplicity index, that permittivity index is invariant at the applying an ambient automorphism, in particular conjugation, but an arbitrary automorphism. The same with the simplicity index. And also, of course, being primitive is characterized by having permittivity index being equal to 1. And being simple is characterized by having the simplicity index being equal to 1. So here is the first sort of geometric statement, which is I'll prove by a picture, which comes basically from a constructive proof of Marshall-Hall theorem. The permittivity index of an element of a free group with a given free basis x1 and xn is bounded by the cyclically reduced length of the element G. So G was a non-trivial element. Well, I have said G non-trivial. So where this is the cyclically reduced length of G with respect to this free basis X. So here is a cartoon picture which explains why this is true. So we start with the commutator A and B, which is, well, okay, there are some controversies in group theory about what the commutator is, but we'll assume that this is A inverse B inverse AB. So it's already cyclically reduced, and if it's not cyclically reduced, we cyclically reduce it first, and because conjugation does not change the permittivity index, so we can always cyclically reduce the element first. So, and then we write it on a circle like this. So here is A inverse B inverse AB. So this is our base vertex. And then there is like a simple observation that starting with the cyclically reduced word written in a circle, you can complete this picture to a finite cover of the rows. You know, this is the rows R2 graph is a single vertex and the two petals labeled by the free basis, in this case just A and B. So you can complete this to a finite cover of this picture by just adding some edges and no new vertices. And in this case, you know, so these are the blue edges that I added, and you see that in order to be a finite cover, you just need to make sure that every vertex has two, I mean, one outgoing A arrow, one incoming A arrow, one outgoing B arrow, one incoming B arrow, and that's the case here. So that will make it into a cover, and you know, so this picture here provides you know, a cover of degree 4 of this R2, and the degree of this cover, because we didn't add any new vertices, is equal to the original cyclically reduced length of the word from which we started. You know, that's what this is, and of course the degree of the cover corresponds to the index of the subgroup represented, or finite index represented by this picture, sort of. So this picture is the Stalling subgroup graph of some subgroup H. So of index, well, in this case of index 4. In general, it will be of index equal to the cyclically reduced length of the element G. And the thing about this construction is because the element G was like a simple circuit from which we started. So in the graph the gamma that we constructed, the circle corresponding to the element G is an embedded circuit. So that translates into the fact that G is a primitive element in the fundamental group of gamma, and therefore in the group H. So here we constructed a group H of index equal to this precisely in this example of index 4, where the element G belongs to the subgroup and where G is primitive there. So that's sort of both a proof of Marshall-Hall theorem and a proof of this inequality as well, right? So that's sort of yes.
Do you have an example where the inequality is sharp?
Yes. So in particular, you know, the main results of the theorem, you know, like over here in theorem A, right? The length of the element is 2ni, but the primitivity index is basically log ni. That's what the theorem says. So it's much smaller. But yeah, so that's one of the interesting features of this theorem. So we'll revisit it, but yes. So in fact, I'll come back to this point because that's actually one of the main sort of interesting proving a statement like that. So I'll mention that later. So let me mention something else, that this notion of primitivity index, it has another motivation coming from the fact that this is a kind of a dual notion to the notion of primitivity rank, which was introduced by Daron Puder in around 2014, maybe a little earlier. I forgot to check the exact date. And that notion is defined as follows. So if you have a non-trivial element in the free group, you define its primitivity rank as the smallest rank of a group H, which contains G as a non-primitive element, if such H exists at all. And you define it to be equal to infinity if no such H exists. So what you see then is that this primitivity rank is either equal to infinity, which actually happens if and only if G was already primitive. So for primitive elements, it's equal to infinity. For non-primitive elements, it's less than or equal than n. The rank of the ambient group. And somehow the bigger it is, the closer it is to n, the more non-primitive the element is, the further away it is from being primitive. So this is this primitivity rank is also some kind of measure of non-primitivity. And it turns out that this primitivity rank plays an important role in various recent results about coherence of one-related groups. So this started with the work of Weiss, the papers of Lauder and Wilton, Heiken and Linton, who actually produced finally a proof of coherence of one-related groups, of all one-related groups. Lauder and Wilton did it for one-related groups with torsion, and then Heiken and Linton for torsion-free one-related groups. And primitivity rank, is a key concept in the proofs of those results. But one thing to mention here is that even though both primitivity index and primitivity rank somehow measure non-primitivity of an element, primitivity index is in some sense, it's more quantitatively sensitive because at least it takes infinitely many values, while primitivity rank actually has only finitely many possibilities, right? There is infinity and there are finitely many values here. It's always less than or equal than n. So apart from just primitivity index and simplicity index of individual elements, you can also form this worst case functions where you maximize the primitivity index of all elements of length less than or equal than n for reasons of avoiding some sort of stupid counterexamples. One needs to take elements which are not proper powers, otherwise the behavior of the function becomes non-interesting. And the same thing with simplicity. So fsimp, you take the maximum of this simplicity index over all elements of length less than or equal than n, which are not proper powers, and you get worst case sort of functions. And because of what I told you earlier, there is this kind of relationship between them. And so in my paper with Neha Gupta, so we proved a bunch of things about these things. So we showed that these quantities, the primitivity index and simplicity index, they were algorithmically computable, even though it's actually hard, so there is like a there are parts of the algorithm which I think are very difficult to implement, but at least abstractly, the thing is computable. So we also studied how these notions behave on random elements. So we proved that for elements of the free group generated by simple non-backtracking random walks, the primitivity index and simplicity index, they basically have this kind of essentially logarithmic lower bound. There is a cube root here for a certain reason. Also the absolute worst case behavior for these functions is basically logarithmic, divided by something log n. And moreover, for the primitivity index function, so Khalid Urabi, so in an appendix to our paper, so he related the primitivity index function for the free group to the residual finiteness quantitative function, whatever it is called, I forgot, for the free group. And using that, he showed that there is a lower bound which looks like that, which is sort of like n. I mean, it's like n to the power 1/4 or something. And if one assumes that a certain conjecture about Cayley graphs of finite groups holds, then one gets a bound which is almost linear. So one gets a better bound. And I mean, it's not quite clear what the actual lower bound for this function is, but it should probably be either linear or close to linear. So this is probably, quite close to the truth. But in any event, that's what's known. For the simplicity function fsimp, nothing better than this is known, even though probably the actual worst case behavior must be far from being logarithmic, but well, we don't know. Answering your question, so one of the interesting things is that this proof of Marshall-Hall theorem, it somehow creates the following problem. On any explicit sequence of elements that you construct, it always tends to be the case that either this primitivity index function, let's say, for some stupid reason becomes bounded, or even one, or at least some bounded number, or it's linear in terms of the length of the element, like it was linear in our example. So it's very hard to make it anything intermediate. So it's actually hard to construct any explicit sequences where this dsimp behaves in a way which is sublinear, but it's not bounded by a constant. So it tends to either collapse to a constant or it tends to stay linear, because that's sort of how the proof goes, and it's hard to make it anything else. So, and when we realized this, so we thought, okay, can anything sort of else happen? And one of the questions that we asked is, what happens with this particular very simple sequence of elements? So in the free group of two generators, and we didn't know. It wasn't even clear whether the sequence is bounded. And when you start thinking about it, you realize that it's it's not this kind of questions, they don't have obvious answers. You have to do something, and it's not quite clear what it is. So the first result of this talk sort of answers this question. So this sequence is unbounded, and we exhibit a specific subsequence in which it has this log n behavior. This is when n is LCM of the first numbers 1 through I. So let me say something about a little bit of number theory that goes into this. So there is like a small amount, but nevertheless we need something. So before I do that, so usually when you see some results which involve number theory and there is a free group of rank 2 involved, there is a tendency to think that this is some kind of a rank 2 phenomenon, but actually, in this case, it's not. We were just a little lazy, and we proved our result for rank 2 because it was cleaner to write a proof. But the CM1 or CMA, was it? It's not really about the free group of rank 2. So if we took a free group of rank 3, A, B, and C, and sequence A to the N, B to the N, C to the N, the same conclusion would have been true, and the variation of the proof would still have worked. So this is not a rank 2 phenomenon.
Does this rank stay the same or change? Like add the generator, keep the word the same?
So it is important that the exponents are the same. So
no, if you take the word A to the N, B to the N in FABC, is it the same or different?
I'll have to think about it. I think that for the primitivity rank, it's probably the same. Yeah. So the simplicity rank is already, going to be equal to 1 on the nose, but for the primitivity rank, I think it will be similar behavior. Yeah.
And for higher, it has to be like ABC. You cannot skip one.
What I mean to say for the moment, I just want to say that it is often the case that when like some kind of a connection like this with number theory emerges and the result is stated for the free group of rank 2, it seems to suggest that this is specifically a rank 2 behavior, and I want to say it's not. We were just a little lazy in terms of writing it down, but we wanted to have an example. It seemed more interesting, but we could have proven a more general result if we were less lazy. So yeah, so what do we need from number theory? You know, not much. We need something about the Chebyshev function, which is log of LCM of so P of m, second Chebyshev function, logarithm, natural logarithm of LCM of the numbers 1 through m. And the main thing that we really need is something about the asymptotics of this function, that this P of m is equal to m to plus little o of m. You know, that's what we need to know as m goes to infinity. And as a consequence of this fact, you know, which I don't know, so ultimately goes to some kind of antiquity, you know, so even though, so in this form, it may be not all that old. So we needed some reformulation of some consequences of this statement, which I'll tell you about in terms of smallest non-divisors. So if you have an integer n, so by d of n, I'll denote the smallest integer d greater than or equal to 2, such that d does not divide n. So this is a very specific number which you can associate with any n. And let me state, you know, proposition number 0. So if n is greater than or equal than 3, and d is this d of n, then first of all, one can show, you know, this is like a little check that this d is going to be bigger than 1 and smaller than n, d of n. And second, as a consequence of this fact over here, you know, so I'll not show you why, but I mean, it really comes out of sort of playing with this fact, so that this d, it has upper bound, which is log n plus a constant, and which is true for every n. And if you take n to be LCM of numbers 1 through I, then it has a lower bound of the type log ni. Well, I wrote here minus O of log ni, but you know, so it's a little frivolous. I could have written here d is equal to log ni, you know, plus a little O of log ni, but you know, you should think about this as a positive quantity. So the upper bound is log n plus c. This is true for all n, and lower bound is for ni of this form. So that's what comes out of this statement, properly processed. So now let me explain sort of two parts that go into theorem A. So theorem A, remember, said that this primitivity index function of this ANI, BNI minus log ni, that this was little o of log ni, right? So in order to prove this, so we'll prove an upper bound and a lower bound. And an upper bound will be easier, a lower bound will be a little more fussy. So, and an upper bound will also be more general, actually, you know, so, but a lower bound will be specifically for n of that form. Okay. Wow. Where I was. Okay. So I want to explain this proposition that for all n greater than or equal than 1, now not only for ni of this form, primitivity index of an b to the n is less than or equal than log n plus c. So let me try to explain why this is true. So now I take this element wn, a to the n, b to the n, and I take, let's say for n greater than or equal than 3, and I take d of n, which is d, that's going to be the smallest non-divisor of n, the smallest d greater than or equal than 2, which doesn't divide n. And by this proposition 0 from before, we know that this d is bigger than 1 and less than n, and it's less than or equal than this log n plus c, where c is a constant from this proposition 0, right? So now what I do, what we want to do is we want to write, divide n with the remainder by d. So we write n as k times d plus r, where k is the quotient and r is the remainder. So r is bigger than 0 and less than d, the remainder. And now I'm going to create a very specific subgroup H of finite index with which I'm going to play. So it's going to look like this. So here it's going to be a cycle of A's of length d, so which flows clockwise, and a cycle of B's also of length d, which flows counterclockwise like this. So you can see here that this graph really does represent a subgroup of finite index, because at every vertex we have one outgoing B arrow, one incoming B arrow, one incoming A arrow, one outgoing A arrow. So this is a subgroup of finite index, and because the graph has D vertices, so this is a cycle of length D, so this is a subgroup of index D. This graph represents a subgroup of index D, and I claim that one can sort of play with this graph, so and see that this. I'm not going to sort of show you the details. That this H has the following three bases. So it's a basis of consisting of D plus 1 elements, and they are A to the D, and then AB, A squared, B squared, A cubed, B cubed, up to A to the power D minus 1, B to the power D minus 1, and B to the D. So you have to sort of choose appropriately a maximal tree. Let's say all the A's except for the last one, look at the dual basis, and then you have to do some kind of Nielsen transformation on the resulting three bases, and then you get this. So there is a little bit of work involved here, but ultimately you can find that Y is going to be a free basis of this H. And then, so one can write down Wn, which is our word A to the N, B to the N, as a word in this free basis Y of H. And let's see how this works. So remember N was K times D plus R. So we write it as A to the D times K, then A to the R, then B to the R, then B to the D times K. And in these new generators, of H, so this is Y0 to the K, YR, YD to the K. This is, first of all, an element of H, and moreover, this is a primitive element of H because the free generator YR occurs in this expression exactly once. So, and then when you have a word in the free generators, where some generator occurs exactly once, that's a primitive element. So we found a subgroup of index D, which contains this element Wn, and where the element Wn is primitive. That means that the primitivity index of Wn is at most D. And by this number theoretic thing, we know that D is less than or equal than log n plus C. So we get this inequality, and that's what was being claimed as an upper bound. Okay. So that was nice and easy, relatively speaking. So how about the lower bound? So a lower bound is a little more fussy. So there will be some lemma, which is a little more involved, actually. Ultimately, in terms of proof, it's fairly unpleasant. And that's why I will not show you the proof, but it's not really sort of anything transcendental. So let me sort of tell you the statement that if you have a subgroup of finite index P does not have to be a prime. It's just a finite index P in the free group on A and B. And now you pick K less than or equal than P and L less than or equal than P, their smallest positive integers, such that A to the K and B to the L belong to H. I mean, of course, when you have a subgroup of index P, such K and L exist, right? So for any elements, not just for A and B, but for any elements, so there will be some power less than or equal than the index, such that the element belongs to the subgroup. So we pick the smallest ones for A and B. So these are, going to be K and L. And the claim is that then there exists a free basis of H, which is called Y, such that A to the K and B to the L simultaneously belong to Y. So, as I said, the proof is a little fussy, but what you have to do is you have to look at the subgroup graph for H, where you can see sort of the cycles at the base point labeled by A to the K and B to the L. And there are sort of two cases, one is easier than the other. The first case is where the only vertex in common that they have is the base vertex, where this statement becomes fairly easy. And the other statement is where they have some other common vertices, where then you have to analyze combinatorially what happens, sort of play with some appropriately chosen maximal tree and the dual basis, and then do some Nielsen transformation and get the statement. So there is a little bit of combinatorics involved, but ultimately there is nothing here that is that requires any sort of deep machinery. So it's basically working with storing subgroup graphs to get the statement. So let's say that we believe this. So now I want to prove the lower bound statement, which says that if we have I greater than or equal than 3 and ni is going to be LCM of numbers 1 through I, then the primitivity index of a to the ni, b to the ni is going to be greater than or equal than d of ni, and by the other number theoretic fact that I told you, d of ni, so this is the stuff that comes out of this Chebyshev function business, d of ni is greater than or equal than log of ni minus O of log of ni. So that's where the lower bound will come from on that subsequence. Okay, so let's prove this. So we put di to be d of ni, and we take H to be a subgroup of finite index where the index is equal to M, and we assume that this index M is strictly smaller than this di. So, and suppose that it so happened that Wi, which is the element A to the Ni, B to the Ni, belongs to the subgroup H. So we aim to prove now that in the subgroup H, this hypothetical subgroup H, the element Wi is not going to be primitive. So if you prove that, it will imply that the primitivity index is greater than or equal than d of ni, right? By definition. So that's how the argument will go. So let's see how to do this. So we choose these elements k less than or equal than m and l less than or equal than m. So to be the smallest, such that a to the k and b to the l belong to h. And now by this lemma, there exists a free basis of h, such that a to the k and b to the l belong to y, the free basis of h. And now I'm going to try to write down this element Wni in this free basis and see how a to the k and b to the l participate. So remember now, Ni is actually a multiple of both k and l, and because we chose m to be smaller than di, so that actually means that k let me see, so m is strictly less than, yeah, so what do you want to say here? Di was the smallest non-divisor of the number Ni, and k and l are smaller than that, so they must be divisors, right? So this means that k and l, they both properly divide Ni. They're smaller than Ni, which means that Ni is equal to pk and ql, with both p and q greater than or equal than 2. So that's what we are going to use. And what that means is that when we look at our element, which is a to the power ni, b to the power ni, and when we rewrite them in these generators, free generators from y, a to the k, b to the l, so we are going to write them, so this one of them was called y1, I think this is the one which was called y1. I'm not sure where, but did I write somewhere that this is y1? If I didn't, so. This is y2. When we expressed our element Wni in terms of these generators, so it becomes y1 to the power p, y2 to the power q, where both p and q are greater than or equal than 2. And the other free generators don't participate at all, but it doesn't matter. So after this, so the fact that both p and q are greater than or equal than 2 by some kind of standard Whitehead graph argument implies that this element Wni is not primitive in the free group with the basis y, which was our subgroup H. And that's what we wanted to prove. We wanted to prove that it's not primitive there, which by definition of primitivity index means that the actual primitivity index of the element Wi must be greater than or equal than di. So it cannot be equal to m. It must be greater than or equal than di. That's what's written here. So it's greater than or equal than d of ni, so which is greater than or equal than log of ni minus little o of log of ni. So that's how the lower bound in theorem A is proved. So, and as I said, proposition 1 together with proposition 2, they imply proposition A, right? So proposition A, once again, theorem A, so theorem A, what did it say? So let's go back to it. So it said that this sequence is unbounded, and specifically on the sequence A to the ni, B to the ni, where ni is LCM of the numbers 1 through I, the difference between this primitivity index and log ni is little o of log ni. So what we actually proved is a little more precise. What we proved is that this primitivity index is less than or equal than log ni plus a constant and greater than or equal than log ni minus little o of log ni. But nevertheless, what's written here sort of is still true. So theorem B says that for the simplicity index, you always get 2, right? So the behavior is different. So let me tell you why. This is actually, well, if I can only find the corresponding slide. Yeah. So let's see why this is true. So the simplicity index of A to the n, B to the n is equal to 2. So there are two cases. So they're actually going to use the same subgroup here for analyzing what happens. And this is just going to be a subgroup of index 2. And it's this subgroup of index 2. We have sort of already seen it. So this is going to be the base vertex. Oops, no, I didn't want to do that. So this is going to be our base vertex. So here is a cycle of A's of length 2. Here is a cycle of B's of length 2. You can see that this is a subgroup of index 2 in the free group of rank 2. And using the lemma that we discussed, you can also check that A squared, AB, and B squared is a free basis for it, right? So we are going to use this free basis, and now we are going to consider two different cases regarding the parity of n. So if the parity of n is odd, then in fact we can use one of the previous lemmas, because it will say that n equals 2 is the smallest non-divisor, right? And remember we proved that. Well, I mean, okay, there was some constant c that was sort of present there. Now we are going to use the same argument, but more precisely. So if n is odd, then n is equal to 2k plus 1, and we can write this element wn, which is a to the n, b to the n, as a squared to the k, a b, b squared to the k, and in these generators over here, this is y0 to the k, y1, y2 to the k. So this belongs to H, and this is actually a primitive element of H. So this is a primitive element in this basis, and in particular, it's a simple element also. And since well, it's simple, the simplicity index is less than or equal than 2, because we exhibited a subgroup of index 2 which contains this element as a simple element. And the simplicity index is not equal to 1 because in order for it to be equal to 1, it would have meant that the element Wn belongs to some proper free factor. And once again, some kind of a weighted graph argument rules that out. So one can show that this element Wn does not belong to a proper free factor in the free group of rank 2. So this is a weighted graph argument. So the simplicity index in this case is precisely equal to 2. It's not less than or equal than 2, it's equal to 2. And if n is even, then well, n is equal to 2k, and we get something even easier. So a to the n, b to the n is equal to a squared to the k, b squared to the k. So it's y0 to the k, y2 to the k. Okay, so it again is an element of H. It's no longer primitive, but it is a simple element in the free group H, because it emits a free generator. Remember, H was a free subgroup, is a free group on y0, y1, and y2. And here we've gotten a word which emits the free generator y1, right? So it emits the free generator y1, and that, therefore it belongs to a proper free factor of H. It's a simple element of H. And that means that we found a subgroup of index 2, which contains Wn as a simple element. So once again, that implies that the simplicity index is less than or equal than 2. And once again, the Weighted graph argument tells us that it's equal precisely 2 and not 1. So we are done with theorem B. So as you see, it's pretty simple. There are some other results in this paper of slightly more sophisticated nature, which use some other graphs that I showed you, other than the ones which I showed you, where you have to do a little more work of more sophisticated kind. But nevertheless, I mean, this already shows you the flavor of the arguments and what kind of stuff one has to do. And you see here that, okay, something slightly interesting happens, especially where somehow one has to use the tool from the outside to sort of to estimate these degrees using some number theory. So let me mention some questions, a few questions that remain open. There are actually very many, but you know, so here is some kind of a random sample. So even for this very specific sequence, a to the n, b to the n, where, as I said, you know, so before the question was, is the sequence unbounded? So now we know that it is unbounded, but that still does not quite explain what sort of the real asymptotics of the sequence is. In particular, are there any subsequences where it grows faster than the logarithm? So we found one where it basically grows as log n, you know, so is that the maximal possible growth? Probably yes, you know, I think probably yes,
It's
but
2 generators, right? Probably if it's more generators.
I mean, one can ask the same question for you know, for more generators, but I think that I mean, the basic case to understand here is the case of 2 generators. Probably whatever one figures out here will be the general case, you know. So I mean, I expect that probably what we found is the fastest growth, but I mean, this requires proof. I don't know, you know, so I mean, we don't have like a formal argument for it. What I think is also more interesting, as I said, sort of in some sense, the motivation for this entire thing was to find explicit sequences of elements where the behavior of the primitivity index is somehow intermediate. It's not linear, it's not constant. And we found something where, okay, it's some kind of a logarithm, but I mean, let's find something else, maybe like square root of n or n to the power alpha, where alpha is something else, some other number between 0 and 1. And I don't know whether it's possible. I mean, I hope that it's possible. It should be possible, but the question is how to do it or where to even look. And as I said, it's there are issues here with both upper bounds and lower bounds. Even upper bounds are in fact non-trivial because all sort of standard ways of producing upper bounds tend to produce linear upper bounds. I mean, it's hard to do anything else. And the moment your arguments start producing something other than linear upper bounds, they tend to produce constant upper bounds. So that's sort of what happens in this business. So it's hard to do anything else with at least explicit examples. You know, so as I said, for this worst case function measuring the simplicity index with respect to the length of the element, the lower bounds are not at all understood. So there is the results of Burabi show that for the primitivity index function, at least modulo some conjectures in finite groups, there is something which is very close to linear. And for here, the only thing that we proved with Neha Gupta was something like C log n over log n, which is probably very far from like the actual worst case behavior of this function, I think. I mean, I would like to believe that it's also linear, you know, or close to being linear, but we don't have that. Who knows? So also there are questions about how both of these functions really behave on random elements, even on random elements, like in the simplest possible sense, where you do a simple non-Bakatian random walk on the free group with respect to free basis, or if you don't like it, you just pick uniformly random element from the sphere of radius n in the free group of that. And as I said, the kind of bounds that we produced with Neha are basically logarithmic, the lower bounds, which I also, and even that required some kind of fancy sort of stuff from probability theory, some kind of like a phase transition tool for the law of large numbers. But I personally don't believe that this is the true behavior. I mean, somehow it should be linear, I think, but I mean, proving that the behavior even of the primitivity index function on random elements is actually linear, I mean, it will require some kind of a really new idea and a new tool compared to what we used here, and I don't know how to do that. So, like, as I said, proving that the primitivity index function behaves linearly or maybe almost linearly on random elements, that's interesting. I don't know how to do it. So then there are open geometric questions in the original context of untangling curves on surfaces, because Gaster's construction that I mentioned about worst case estimates for the minimal degree of the cover where the curve untangles to a simple closed curve. The interesting thing about his construction was that the sequence of curves that he used, there were non-filling curves to begin with. They were very kind of narrow. They lived in a very small subsurface of the original surface sigma. And already in our paper with Neha Gupta, we defined a different degree for a curve where instead of lifting it to a simple closed curve, we look at the smallest degree of a finite cover of sigma where alpha lifts to a non-filling curve. So we don't, the curve still may be allowed to have self-intersections, but if it lives in a proper subsurface, we are happy. So we just want the smallest degree of a cover where the curve lifts to a non-filling curve. So that's a priori smaller than the other degree. And in fact, it's often actually smaller. So in particular, if you start with a non-filling curve already, so this non-filling degree is already equal to 1, while this degree, so if the curve has self-intersections, it will be bigger than 1. And as I said, Gaster's construction does not prove anything at all about the worst case sort of measure based on this non-filling degree, because he already uses curves which are non-filling to begin with to get his linear lower bound. And so how this worst case thing behaves, we basically don't know. And yeah, so as I said, Gaster proved that this thing behaves sort of linearly in the length of the curve, the worst case measure for closed hyperbolic surfaces, but he used non-filling curves. So his argument does not tell us anything about this function. And so it remains sort of interesting to understand the behavior of this function. And I should mention here that in our paper with Gupta, so we produced a lower bound for this function, but only for hyperbolic surfaces with boundary. And so first of all, our bound, only works for hyperbolic surfaces with boundary. And second, even for those, our bound is pretty big. It's basically logarithmic, which is probably far from the truth. But for closed hyperbolic surfaces, no lower bounds at all for these functions are known. Nothing, so it would be interesting to understand at least something. So in this geometric context. All right, so I think I'll stop here. Thank you very much.
Are there any questions?
So if you look at this inequality again, that primitivity index is less than or equal to n, well, less than second length. So if you change bases, length may go down. So like, do you know if like equality can only be achieved, or like what's the
So I mean, it's true that I mean, you may as well assume that the element was sort of minimal. I mean, so in some sense, yeah, you're right. You can. The interesting part of this inequality has to do with elements which are automorphically minimal with respect to your free bases. That is true, yes. But I should say that random elements are automorphically minimal, at least cyclically reduced ones. So at least over there, there is no difference. So you are correct, but somehow for most of the questions that I was discussing, that doesn't sort of seem to help. So, and in particular for the sequence A to the n, B to the n, that doesn't really help. So you can't really shorten it.
vague question?
Yeah.
Do you think there is any connection with compressed length?
I haven't thought about it. I mean, possibly one never knows. So, I mean, I don't see it right away, but there is possibly something because I mean, there are some certain things having to do with performing sequences of collapses on stalling subgroup graphs with some. So there are some problems which appear both here and in some problems when you start thinking about complexity of you know, of compressed problems that sort of appear in both cases. But other than that, I don't know. So hard to say.
More questions, probably from the audience.
Yeah, so let me see. I have no idea what's happening here. Find chat. No, nobody's happy.
I mean, questions, probably they don't hear me.
Well, I mean, I guess we'll find out after the talk whether anybody heard anything. You know?
No, we hear.
Yeah, it worked. Yeah, it worked.
Yeah, yeah,
More questions?
I hear too. I hear too.
Thank you, Ilya. Cheap party, water for people who want to have wine.